Beneath a calm surface, a humpback whale begins exhaling while swimming in a rising curve. The bubbles form a pale wall, wrapping schooling fish inside a shrinking circle. Moments later, several whales surge upward through the center with open mouths. The structure is called a bubble net, although nothing solid restrains the prey. Its power comes from behavior, geometry, sound, and the defensive instincts of schooling fish. The mystery is how enormous mammals construct a temporary trap from air they cannot retrieve. Each breath spent below removes oxygen from a dive already limited by physiology. Each turn must match prey movement within dark, turbulent water. If you watched from above, the spiral might resemble a deliberate drawing. Below the surface, currents deform it while fish search for an escape. The whales must create enough confusion and concentration to repay the cost of the maneuver. Some hunt alone, while others join groups whose membership and tactics can change. The bubble net is therefore neither an automatic instinct nor one universal choreography. It is a flexible feeding technique observed most clearly in particular populations and seasons. Every successful lunge begins with finding prey dense enough to justify the design. The humpback whale, Megaptera novaeangliae, is a baleen whale with long pectoral fins. It feeds on schooling fish and krill in productive high-latitude and coastal waters. Rather than teeth, overlapping baleen plates filter prey after a mouthful of water is engulfed. Expandable throat pleats allow the lower mouth region to balloon during a lunge. That expansion creates tremendous drag, so poorly aimed lunges can waste substantial energy. Concentrating prey before engulfment can make each costly acceleration more profitable. Herring commonly feature in documented bubble net feeding in parts of the North Pacific and North Atlantic. Other schooling prey can also be targeted, depending on region and season. Whales locate patches using hearing, vision, memory, and responses to nearby feeding activity. Direct observations and attached tags reveal dives, rolls, accelerations, and coordinated ascents. Hydrophones record feeding calls associated with some group bubble net sequences. Drone footage can reveal bubble shapes near the surface, though it misses deeper beginnings. Combined records show that one whale may descend beneath the school and start a curved ascent. It releases bubbles in a controlled stream while turning around or beneath the prey. The rising bubbles create a moving visual and mechanical boundary in the water. Fish often tighten their school away from that boundary, reducing the space they occupy. The cue is the bubble curtain. The action is inward schooling, and the consequence is concentration. The whale may complete a ring or a spiral, depending on prey and local technique. Other whales position below the gathered fish and orient toward the central opening. Some groups produce a loud, rising feeding call before the final ascent. That sound may help drive or concentrate fish, although its exact function remains debated. At the critical moment, the whales accelerate upward and open their mouths into the school. They break the surface together or in close succession, then strain captured prey through baleen. The observed sequence is clear, but internal decisions and assigned roles are harder to establish. A spiral net begins as exhaled air divided into many buoyant bubbles. As those bubbles rise, surrounding pressure decreases, and their volume can expand. The curtain also sheds vortices and disturbs water, making it more than a bright visual line. Fish approaching the boundary encounter bubbles, noise, turbulence, and rapidly changing neighbors. You could call it a wall, only if you remember that frightened prey help build the wall themselves. The net works because schooling rules turn individual avoidance into collective compression. If fish calmly crossed the bubbles, the structure would lose much of its trapping effect. Whales can tighten the spiral as they ascend, matching a school that contracts upward. Tag data sometimes reveal precise rolls and banking movements during this construction. Those maneuvers position the blowhole's bubble stream while keeping the body on a curved path. Long pectoral fins may assist maneuvering, but bubble net geometry cannot be attributed to fins alone. The whale must also time its ascent so bubbles reach useful positions before dispersing. Strong currents can stretch the curtain, while deep releases create longer rising paths. Prey depth matters because fish beyond the ring's vertical reach may escape below it. Light levels may change the contrast of bubbles and the reactions of the school. Repeated nets can differ in radius, bubble spacing, ascent angle, and number of participating whales. That variation indicates adjustment rather than a single fixed motor program. Some solitary humpbacks produce bubble rings and feed through them without partners. Group hunts can include individuals that blow bubbles, call, herd, or lunge from particular positions. However, named roles may oversimplify behavior that changes across attempts and groups. Association does not prove permanent teams, because humpback feeding groups can be fluid. Researchers, therefore, compare repeated sequences before describing specialization or cooperation. Success is inferred from engulfment and prey capture, but exact intake is difficult to measure. Failed nets are scientifically valuable because they reveal which geometry or timing does not work. The strongest interpretation treats bubble netting as learned, flexible foraging supported by social opportunity. Bubble net feeding connects individual intelligence with the seasonal physics of prey concentration. Humpbacks migrate long distances and must rebuild energy reserves on productive feeding grounds. A dense mouthful of herring can help finance travel, thermoregulation, and later reproduction. The technique becomes especially valuable when prey respond predictably to disturbance. When herring dive, scatter, or form looser schools, whales may alter the net or abandon it. The cue is changing prey density. The action is tactical adjustment, and the consequence is reduced wasted lunging. Young whales can observe feeding adults and may acquire local methods through social learning. Population differences in technique are consistent with cultural transmission, though learning pathways remain under study. If you hear repeated feeding calls, they indicate patterned behavior, not a translated command language. Sound recordings become stronger evidence when synchronized with tags, bubbles, prey, and individual positions. Fisheries and whales sometimes depend on the same schooling fish, creating shared sensitivity to stock changes. Reduced prey density may make elaborate netting less profitable even when fish remain present. Ocean warming can shift plankton production, fish distribution, and the timing of feeding aggregations. Entanglement in fishing gear threatens whales working within productive coastal zones. Vessel traffic adds noise that may mask communication or alter behavior, depending on distance and intensity. Understanding feeding choreography can help identify places and seasons where disturbance carries greater cost. It can also prevent surface spectacle from hiding the energetic constraints below. The behavior is remarkable precisely because it remains tied to prey, ecology, and limited breath. Air is abundant at the surface, but every bubble carried downward has a physiological price. The whales pay that price only when their temporary architecture improves the coming mouthful. Future studies need simultaneous views of whales, bubbles, currents, and prey throughout complete dives. Multi-sensor tags can measure depth, acceleration, orientation, and sound on individual participants. Upward-looking sonar can map prey movement, though echoes require careful interpretation and ground truth. Drone imagery can measure surface geometry when visibility and regulations permit safe observation. Together, these records could test whether tighter spirals consistently produce denser prey. They could reveal how one whale changes its path when another arrives late. You might then see coordination emerge through adjustment, rather than through rigid leadership. Researchers also need data from failed hunts, solitary nets, and populations using different techniques. Long-term studies could show how young whales refine movements across successive seasons. Researchers still do not know how consistently age and group history shape each whale's technique. The next breakthrough will probably come from synchronized evidence, not a more dramatic surface image. It should separate what bubbles physically do from what frightened fish collectively make them do. It should also explain when a spiral is better than a ring or no net at all. Until then, cooperation remains documented in movement, while its moment-to-moment communication stays partly unknown. The opening circle now closes, and dark fish flash inward before the whales rise. A humpback bubble net is a measured, learned use of breath that concentrates real prey without ever becoming a solid net.